Hello everybody, welcome back to yet another video of FikarNot.com, now FikarNot from studies. So today we are going to be talking about carbon dioxide. What exactly is carbon dioxide? How is it related to us in our life? And what is the importance that carbon dioxide holds in our lives? Basically, the same question. Is life exactly possible without carbon dioxide? I think you all will say no, because plants cannot live without carbon dioxide, and without plants, we cannot live because we will have that suffocation. Because where will we get oxygen from, right? Because, of course, plants, after photosynthesis, they produce oxygen. I think you all know that. So, one thing that we know exactly that carbon dioxide is something that we cannot live without. But this is only one reason. Today, we are going to learn several reasons about how carbon dioxide helps us in going smoothly in our day-to-day lives. And how is carbon dioxide present in different forms, be it liquid, gas is carbon dioxide itself, and in a solid state. But before that, in my last video, I talked about coal, peat, anthracite. I talked about animal charcoal, bone charcoal, and wood charcoal. So just a little revision we are going to do over here. So the breakdown of organic substances like coal or wood on strong heating in the absence of air is called as, I think this is easy, right? In the absence of air. Definitely it will be the destructive distillation. Perfect. Which of the following is used to remove brown color of cane sugar? I think we all know that, right? It is bone charcoal. That's right. It is bone charcoal. Bone charcoal is used as a decolorizing agent. I think you guys remember that, right? It is used to remove the brown color of cane sugar. So it will be this will be ticked onto bone charcoal. Then the amorphous form of carbon is used for making kajal is definitely lamp black. I think this is something we all remember. State whether the following statements are true or false. Rewrite the false statements correctly. Okay. Due to high temperature and pressure inside the earth and the absence of air, remains of dead plants slowly converted into coal. It's a big false. Now, for the people who think it's true, well, they say it is in the absence of air, when that is not true. Air is present, or else it would be known as a destructive distillation of the formation of coal. But the coal is formed without the destructive distillation. That's one thing. Then coal is used in thermal power plants to produce electricity. Well, that's a big true. Activated wood charcoal absorbs colored ink from ink solution. That's a false. Destructive distillation of sugar cane produces bone charcoal. No, it produces sugar charcoal. So false. Sugar charcoal is porous, thus floats on water. No, it's actually wood charcoal that's porous and it floats on water. So again, it's a false. And wood charcoal, actually, it does not exactly absorbs colored ink, but it is a good absorber. So we will say that it does absorb colored ink from the solution just because it is a good absorber. So that's my mistake. Actually, activated wood charcoal absorbs colored ink, but that's only activated because it is a good absorbent, definitely, right? So we can say activated wood charcoal absorbs colors from the solution. So that's my mistake. It does. So this one is also a true. Okay, perfect. Now, let's move on to our chapter, carbon dioxide. So, carbon dioxide is a compound made up of one atom of carbon and two atoms of oxygen. That's one thing that we all know, because it is CO2. So, two atoms of oxygen and only one atom of carbon. Right? And carbon dioxide is found in both free and combined states. Over here, you must think that carbon dioxide is a free or it's a combined state, but it's only for carbon. As of carbon, it's a combined state because it is adding up with oxygen. But we are only taking carbon dioxide as a whole over here as one, so we call it in a free state. So carbon dioxide is a free state, but in a combined state, if there is sodium added to it, if there is sulfur added to it, if there is, say, hydrogen added to it, it becomes in a combined state, of course. So in free state, it is found in air, rocks or volcanic regions, and water. In air, it is present 0.03% by volume, and it is also 1.5 it is also 1.5 times heavier than air. So it is present about 0.03% of volume in air, and this is the free state. It is also soluble in water, thus it is found in water in dissolved state. So in combined state, it exists as metallic carbonates and bicarbonates in the Earth's crust. The main minerals that contain carbon dioxide are limestone, CaCO3, that's calcium carbonate, and dolomite, which is magnesium carbonate and calcium carbonate also. So these are the combined states. Again, it exists as metallic carbonates and bicarbonates, because carbonate is CO3, right? And again, carbonates will be CO3, and if there is bi, it will be HCO3, because there will be H in bicarbonates. So this is how it exists. It can also be in a carbonic acid, of course. So this is how it exists in combined states, of course. Now let's get to know about the discovery of carbon dioxide. How did carbon dioxide make a way into our lives? How did we discover carbon dioxide, and how did we discover that carbon dioxide can be found in free state or combined states, or it is found in our air, or the percentage of its volume in the air? There would be some reason that we know all of this, right? And well, carbon dioxide was actually discovered by Jan Baptist van Helmont in 1640. In 1640, Jan Baptist van Helmont, he burned charcoal in a closed vessel, and Joseph Black in 1775 obtained carbon dioxide by the action of dilute acids on metal carbonates. So he took some dilute acids, he mixed it with or put it on top of metal carbonates, and he named it fixed air. In 1783, Antoine Lavoisier studied the gas. He found that this gas is an oxide of carbon. So he exactly studied this fixed air gas, which was named by Joseph Black. And Antoine Lavoisier, he named this gas as an oxide of carbon, and when dissolved in water produces an acidic solution, because carbon dioxide is acidic in nature. And he named it carbon dioxide later on. So this is how carbon dioxide was actually discovered by scientists or by other people, of course. So now let's get to know about the preparation of carbon dioxide. Carbon dioxide can be prepared by any of the following methods. So carbon dioxide has many ways in which we can prepare it, as Joseph Black also said, with taking say metallic carbonates with dilute acid, right? So that creates carbon dioxide as well. And there are many such ways, so let's see. First one is by burning carbon or carbon compounds. We know that be it crystalline or amorphous form of carbon, the carbon compound or element is present in them. Yes, it is solely made up of carbon and only carbon. So what happens is, when such a substance is burnt, let's say coke. We know coke has about 98% of carbon and a few 2% of impurities here and there, right? Be it hydrogen or oxygen. But it does have 98% of carbon in it. So if we burn it in the presence of oxygen, or if we just burn it with oxygen, CO2 plus heat will be produced. Why? Because it has carbon, and we know that even though these forms may have different structures, some may have hexagonal sheet-like structures, some may have tetrahedral structures which form a rigid octahedral structure, some may have hexagons and pentagons, a Buckminster-Fullerene structure of 60 such hexagons and pentagons to form 60 atoms or molecules. Some may have an ungeometric structure. Whatever it happens, the chemical properties will be the same, because whenever they are burnt in the presence of oxygen or with oxygen, all of them will give CO2 plus heat. So carbon dioxide can be made by burning carbon or carbon compounds. So over here we're taking coke plus oxygen, which gives carbon dioxide plus heat. Now this arrow represents gases. Okay, and if you see this means a precipitate. Okay, perfect. Now let's go on to the second one, by heating metallic carbonates and bicarbonates. So Metallic carbonates or bicarbonates are CaCO3 because CO3 is carbonates, and bicarbonates will have hydrogen in them. So we are going to see some examples over here. So CaCO3 on strong heating produces or decomposes into CaO, which is calcium oxide plus carbon dioxide, of course. So one trick I will tell you over here, whenever you see by heating metallic carbonates or by burning carbon compounds or action of dilute acids, any of this, you know that carbon dioxide is going to be produced, right? Or is going to be decomposed from a reaction, right? So let's take the second example that we're doing now. CaCO3. We know that carbon dioxide is going to be one of the products in which this basic compound will decompose into. So CO2, let's take this out. CO2. So there's one oxygen atom left plus CaO. And that is exactly our answer. This way you can remember and not forget any formulas that you have learned. So CO2 will be a common compound that will come as a product or will come when it decomposes into a product, right? So CO2, just take it out of the reaction and see what you have left. Okay, perfect. Let's go on to the next page. Yes. NaHCO3, sodium bicarbonate. So again, over here they are heating sodium bicarbonate, which is HCO3, of course. So 2HCO3. H is there, that means H2O will also come. I think this you know, right? So 2NaHCO3. So one thing we know that CO2 is going to come out of this whole product. CO2. So we take this CO2. There's one hydrogen atom left. Plus, let's take H2O. And as you can see over here, there are actually two carbon atoms present, right? So can we say Na2, fine? CO3 because it's 6, right? So 2, 3, 4, 5, 6, and over here there are two sodium atoms. So it will be CO2 plus H2O plus Na2CO3. For the people who did not understand, I'll explain it one more time. So let's take this out because this is just for balancing purposes. NaHCO3. Fine. CO2 is 1. H2 is 1. What do we have left? We have Na left only, right? Because everything is done. But one thing we notice over here is that H is there, so I told you H2O will be there. Water will be there, right? Because there is H. So one thing that you notice over here is that in H2O there are two atoms of hydrogen. That means you have 2 over here, which comes out to be 3 atoms of oxygen. So you have 3 over here, fine. You have 2, so you have used 1 over here, fine. So you have only 1 more left, and you have 2 Na, that's sodium atom. So what do? You say Na2 plus, sorry, not Na2 plus, sorry. Just Na2, you take Na2. Then what do you have left? You have still 3 oxygen atoms left and 1 carbon atom left. So you say sodium CO3, sodium carbonate. So the total answer would be sodium carbonate plus water plus carbon dioxide. And that will be your final answer. So this is on strong heating, that is why it decomposes. Okay. Next one. By the action of dilute acids on metallic carbonates and bicarbonates. This is what Joseph Black did in 1775. That's right. So the first one would be calcium carbonate plus HCl. Calcium carbonate plus HCl. Okay. I wonder what we can get with this. Let's see. Okay, so we're not going to look at the answer. CaCO3. Plus HCl. Okay. So again, there's H and there is a C, so we know CO2 is going to come out and we know H2 is going to come out. Fine, perfect. So there were three oxygen atoms, so this is completely gone. This whole thing is completely gone, and we see there are two hydrogen atoms, so we added 2 over here. As a result, what happens is we get, so this is also gone because 2 and 2, right? Ca, Cl, 2 was here, that means 2 chloride, 2. So what will be the answer? Carbon dioxide plus water plus calcium chloride. Let's see if the answer is right. And yes, bang on, it is right. So this is how you want to solve it, okay? Let's take the last three, three we have left. NaHCO3, again over here we say CO2 because there's an H again, so H2O. Yeah, so again 3 CO3 is gone, H, so you have to add 2 over here. This is going to be a little hard. Oh wait, I'm very sorry, I'm extremely sorry. I think I wrote the reaction wrong. It is actually NaHCO3 plus HCl. I totally wrote it wrong, I'm very sorry. So we say, oh, this is easy. Okay, HH, that means H2. We take one O from here, H2O. That means CO2 is left. CO2 plus NaCl. That's salt, of course. So sodium chloride. And are we right? And bang on, we are right once again. Let's go to the next one. Na2CO3 plus H2SO4. Let's see. So over here what we do is H2, there are two H, so we'll take H2, we'll take one O plus CO2. So this is completely gone, this is also completely gone. We have Na2SO4, we'll take that only. So Na2SO4, that will be what? Sodium sulfate, of course. And are we right? Let's see. Yes, we are. Perfect. Now let's go on to the last and final one. I hope you are not seeing the answers. I trust you guys. I hope you're doing it along with me and not peeking into your textbook or my background, right? H. Perfect. So again, over here, as you can see, we have actually a lot of hydrogen atoms over here. So we have 1 and 2. Okay, perfect. So let's take this out, 1, and let's take this out. So it will become H2O plus, this is also gone, CO2. So we have CH3COO. Perfect. So what will we do? We'll say CH3COONA, which is actually sodium acetate, because sodium Na and acetic acid, because there is the H3 still there, so we say sodium acetate. So are we right? Yes, we are once again. And that is how you solve these type of questions. Do not get confused whatsoever. If you have any doubts, please post it in the comment section. I'll be more than happy to solve them. Okay? Perfect. Now, let's move on to some laboratory preparation of carbon dioxide. So carbon dioxide is prepared in the laboratory by the action of dilute acid on marble, of course. So dilute acid again, and this is an experiment of metallic carbonates or bicarbonates with acids. So over here we're taking HCl as our acid and we're taking carbonates. So this is like the first reaction that we saw, right? CaCO3 plus HCl. And remember, all of these acids are dilute acids, HCl, all of it. So if you're taking sulfuric acid, it's dilute sulfuric acid. If you're taking HCl, it'll be dilute hydrochloric acid. If you're taking acetic acid, again, it will be something dilute, right? Or acetic acid is not dilute because it is already like that. So let's look at this experiment over here. Aim to prepare carbon dioxide in the laboratory by the action of hydrochloric acid on marble chips, which is CaCO3. So CaCO3, this is it's a limestone actually, but we're taking it in the form of marble chips here. So things needed will be a wolf's bottle. You can pronounce it however you want. I call it wolves because I feel like that's more approachable, but go with what you pronounce it as, okay? So wolf's bottle, a delivery tube, a distal funnel, rubber stoppers, a glass jar, dilute hydrochloric acid, and marble chips, of course. So over here the method is place some marble chips, CaCO3, in the wolf's bottle and set the apparatus as shown. Pour dilute acid into the wolf's bottle through the distal so that the marble chips are completely immersed in the acid. So what they are doing over here, they are taking the marble chips, that's the carbonate, and they're completely immersing it in acid, which over here is HCl. And they are allowing a few bubbles of carbon dioxide to escape as they might contain air and acid as impurities. Then they collect the carbon dioxide gas in a gas jar by upward displacement of air. CO2 is heavier than air because they collect the carbon dioxide gas in the air, and this is by upward displacement because CO2 is heavier than air. I said this as well, right? It is 1.5 times heavier than air, and that is why it can be collected by the upward displacement. So in this whole activity, one thing that we observe is that a chemical reaction takes place between HCl and marble chips. Carbon dioxide is released with a brisk effervescence. So CaCO3, calcium carbonate, with a dilute hydrochloric acid gives CaCl2 plus H2O plus CO2. Hydrochloric acid reacts with marble chips to form carbon dioxide. So a lot of you may be asking some questions over here that HCl isn't the only acid out there. What if we take some other acid like say sulfuric acid, H2SO4? Fine. What if we take that acid? What will happen? So let's look at the products as well that will be formed if we do so. CaCO3 plus H2SO4. So definitely we know H2O is one thing that will form, CO2 is one thing, and there'll be CaSO4, that's calcium sulfate will be formed. So the calcium sulfate that will be formed instead of CaCl2, CaCl2 is soluble in water, while calcium sulfate that is formed during the reaction will not be soluble in water, it will be insoluble. Therefore, it will cover the marble chips and it will stop the reaction. So, for all those of you who have these questions about why it is used, well, this is why it is used, because the sodium sulfate that will be there, sulfuric acid. I'm extremely sorry. The dilute sulfuric acid that will be used is insoluble in water because sulfuric acid with calcium carbonate will form calcium sulfate, and which that basic compound is insoluble in water. So it will stop, it will cover the marble chips, of course, right? And marble chips, CaCO3, are also preferred over other metallic carbonates because it is very, very cheap, and a lot of people who want to create carbon dioxide and they do not have the money for it, it's more better, especially for schools as well, because all their funding cannot just go in getting expensive things, of course. So they go for a little more easier or a little more cheaper one, which is also again cheap, and it does the reaction perfectly. There isn't any difference, right? And carbon dioxide again is fairly soluble in water, so it is not collected over the water, and this is one of the tests. We can also say why carbon dioxide, how do we know the gas formed is carbon dioxide? Well, this is because carbon dioxide is fairly soluble in water, so it is not collected over water. So this is these are one of the tests that we know that the gas that is collected is CO2 itself. Perfect. Now we are done with all the preparation of carbon dioxide formulas, experiments, and everything. Now we're going to go to some written things like physical properties of carbon dioxide. So let's start with that. So some physical properties of carbon dioxide include its nature, density, solubility, and solidification into dry ice or liquefaction. So first, nature is that carbon dioxide is an odorless and colorless gas. Definitely, because every gas is colorless and it is odorless as well. At room temperature, it is non-poisonous, but more of it can cause suffocation because we take out carbon dioxide of our body, we only take in oxygen. So definitely it is one common thing, and it is just common sense that if there is too much of carbon dioxide in a room, it will be more likely, definitely, for the suffocation to be felt. But it is a non-poisonous gas, of course. Moving on to the density, it is 1.5 times heavier than air, as I've already said in the beginning of this lesson as well. And at normal temperature and pressure, actually, carbon dioxide is 1.5 times heavier than air. Its solubility is that it is soluble in water. Definitely carbon dioxide to prepare all the plants. So even the plants that are present underwater, they use dissolved carbon dioxide present on the water or mixed in the water, and they use that for their photosynthesis, of course. Fourth is liquefaction and solidification into dry ice. Carbon dioxide is actually present in the form of dry ice in its solid form. So carbon dioxide can be liquefied under high pressure to obtain liquid carbon dioxide. When liquid carbon dioxide is cooled up to minus 78 degrees Celsius under normal pressure, it changes into a snowy white solid called dry ice, which is very dangerous to touch with our naked hands as well. So first, that it can be liquefied under high temperature and pressure, or you can just say high pressure, but when it's cooled up to minus 78 degrees Celsius, it creates dry ice. Dry ice can clearly or just directly change into gaseous carbon dioxide without passing through its liquid state. In other words, dry ice sublimes. Definitely, if you've seen dry ice, whenever you open it, there'll be some gas or fumes coming out of it. That's because without doing any process, without going under any process, it can just sublime. And in other words, dry ice, again, it sublimes and it has a cooling effect. Therefore, it is used to produce a false effect of clouds on the stage, because it looks like clouds, the fumes that are just coming out without any process. So it's almost like magical to see it, because it just sublimes without anything. So that is why it is also used to produce a false effect of clouds on the stage. So if you come across a question saying that why is dry ice used to produce a false effect, well, it is because it sublimes and it also has a cooling effect. Now on to some chemical properties of carbon dioxide, about its reaction with litmus paper or water, etc. We will be going on to that, followed by the test for carbon and the uses of carbon, of course. So first, let's start off with the chemical properties of carbon dioxide. So first chemical property of carbon dioxide is that it is combustible. When a burning matchstick near the mouth of a gas jar containing carbon dioxide is brought, it extinguishes, because carbon dioxide neither supports combustion and it is not combustible as well. But some metals like sodium, potassium, and magnesium continue to burn in the presence of carbon dioxide, of course. Then the second chemical property is its action on litmus paper. Carbon dioxide turns a moist blue litmus paper red, because carbon dioxide is acidic in nature, as I said earlier as well. So moist blue litmus paper turns red. And whenever carbon dioxide also, like dissolved carbon dioxide, which forms a really very weak acid called the carbonic acid, definitely, H2CO3, carbonic acid also turns blue litmus red, which shows that this solution of carbon dioxide in water is also acidic in nature, along with carbon dioxide also being acidic in nature, of course. So CO2 plus H2O gives carbonic acid. It is acidic in nature. So whenever, dissolved carbon dioxide is also used, it makes a really very weak gas, but it is still acidic in nature. Then its reaction with lime water is one of the greatest reactions of all time. it is the most talked about reaction. So reaction with lime water, when carbon dioxide gas is passed through lime water, CaOH2, it turns almost like milky. This milkiness is due to the formation of a white precipitate of calcium carbonate. So whenever carbon dioxide, okay, it is passed through lime water, CaOH2, it turns milky. Why does it turn milky? Because a white precipitate of calcium carbonate is formed. So it's like a false milkiness. It isn't actually milk. We cannot drink it, but because of the white precipitate, it looks milky. So CaOH2, which is lime water, plus carbon dioxide. So carbon dioxide is only passed through the lime water, okay? And it forms CaCO3, calcium carbonate, which we also used as marble chips. But in this case, it's a white precipitate plus water. However, when excess carbon dioxide gas is passed, the milky solution turns colorless. This is because of the formation of calcium bicarbonate that dissolves in the solution. So calcium bicarbonate can be dissolved. So if a reasoning question comes saying, if excess carbon dioxide gas is added or passed through lime water, what will happen? Say it will turn colorless because calcium bicarbonate will form, which dissolves in the solution, of course. So CaCO3 plus CO2 plus H2O gives CaHCO3 the whole twice. Calcium bicarbonate is a clear solution. Okay? Perfect. Also, one more thing that I would like to point out is that CaCO3 is already the white precipitate that is formed with water, of course. But when more carbon dioxide gas is formed, all of this together forms calcium bicarbonate. Okay, so just to say, first, lime water plus carbon dioxide will give you a milky substance. But when even more of this is added, or more CO2 is added into the product side, so it becomes a reactance and it gives a final product of calcium bicarbonate, which is a clear solution, which basically dissolves. Okay, now let's go on to the reaction with alkalis. So carbon dioxide reacts with alkalis like sodium hydroxide and potassium hydroxide to produce salt and water. So sodium hydroxide is in alkalis plus carbon dioxide gives sodium bicarbonate plus water. That's Na2CO3. And again, potassium hydroxide plus carbon dioxide will give K2CO3 plus H2O. So it gives salt plus water, carbonate again. So hydroxide plus carbon dioxide will give some type of carbonate plus water. So potassium hydroxide, that is caustic potash, and sodium hydroxide, which is caustic soda, can absorb a large amount of carbon dioxide. Thus, they are used to remove carbon dioxide. Okay. However, potassium hydroxide is preferred because of better absorbing capacity. On passing excess of carbon dioxide, respective bicarbonates are formed. So Na2CO3 plus CO2 plus H2O. Again, CO2. So what happens is sodium bicarbonate is formed. Okay, and similarly with K2CO3 plus CO2 plus H2O, which gives 2KHCO3. Perfect. Now, metals will be metals like sodium, potassium, and magnesium burn in the presence of carbon dioxide to form respective oxides and black peaks of carbon. So, magnesium oxide and carbon are formed when magnesium plus carbon dioxide are reacted together, when they react together. So, again, metals like sodium, potassium, and magnesium burn in the presence of carbon dioxide, and they form oxides like over here magnesium oxides and black specks of carbon. So carbon is the only element over here. It is in a free state, and that's why it creates black specks of carbon only. Then its reaction with non-metals say that when carbon dioxide reacts with non-metals like red hot coke to produce carbon monoxide gas, it is highly poisonous because carbon monoxide gas, it is not good for our health. So it is highly, you can say poisonous, right? So carbon dioxide plus coke gives carbon monoxide, which is very, very poisonous. So red hot coke is reacted with carbon carbon dioxide, of course, to produce carbon monoxide. And the reaction with metallic oxide say that carbon dioxide reacts with a basic metallic oxide to form metal carbonates, which is Na2O plus CO2, which gives Na2CO3, and MgO plus CO2, which gives MgCO3. So these are metallic oxides, of course, because sodium oxide or magnesium oxide, they react to form metal carbonates because CO3 is formed, right? So just a little a revision from alkalis, because I think before that was all easy. So alkalis, what did we learn about alkalis? That any hydroxide is reacted with carbon dioxide to form water and salt. And as far as metals with carbon dioxide form black carbon. What was it? Yeah, black specks of carbon plus any type of oxide like magnesium oxide. Non-metals like coke with carbon dioxide makes or produces or gives a product of a very poisonous gas called carbon monoxide. And as of metallic oxides, of course, Na2 or like sodium oxides that react with carbon dioxide, they give metal carbonate, CO3. So any type of metal with CO3, because CO3 is carbonates. Now let's look into the test for carbon dioxide and the uses of carbon dioxide. After that, we'll be done with carbon dioxide. Now, some tests for carbon dioxide are when a burning matchstick is introduced in a gas jar containing carbon dioxide, it gets extinguished and carbon dioxide gas turns lime water milky. So these are some tests for carbon dioxide, just saying how carbon dioxide is formed exactly, right? And to say that whatever we form is carbon dioxide and that the gas that we have is carbon dioxide itself. Now, the uses of carbon dioxide are in aerated drinks, as carbon dioxide gas as it is used in aerated drinks. It is dissolved water and under pressure, of course. So what happens in aerated drinks? I think the Coke, soda, which you drink along with your pizza or your pasta, carbon dioxide gas is used in those because it is dissolved in water under high pressure. Because we all know carbon dioxide gas can be dissolved in water. So when it is dissolved in water under high pressure, it forms soda water, and when we open this water or open this bottle, the pressure released and the gas escapes with the brisk efference, and this adds a fizz to the drink, and the soft drinks are formed by dissolving carbon dioxide in a sugar solution, basically. So this is how it is dissolved in soft drinks. So they are formed by dissolving carbon dioxide in a sugar solution. So all of this creates just soda water, and whenever we open the water, it creates this fizz and the gas escapes. So it is used in these drinks, of course. And then the second one is as a refrigerant. Dry ice is used as a refrigerant for preserving foods like fish, meat, ice cream, and vegetables. The grains can be preserved and kept fresh in an atmosphere of carbon dioxide. So the refrigerant, as in the the freezer, or the refrigerator that you have has actually dry ice in it because it preserves the food. That's why we can get frozen foods in the first case. So that is why frozen foods, and that is how they are preserved as also. Then the third one is in the manufacturing of chemicals. Carbon dioxide is used in the manufacturing of baking soda, sodium bicarbonate, and washing soda. Mixture of sodium bicarbonate and potassium hydrogen forms baking powder. Baking powder is used in making cakes and bread spongy as it releases carbon dioxide. So the sponginess that you get, why does your cake bake? It is because of the manufacturing of the chemicals like baking soda, washing soda, or even baking powder. Then in photosynthesis, I think this is something you all know. Plants cannot live basically without carbon dioxide because they need it for their photosynthesis. So yes, this is where it is used. Then in hospitals, carbon dioxide is used in the form of carbogen for artificial respiration. Carbogen is a mixture of 5% carbon dioxide and 95% oxygen. So for the people who have less supply of oxygen in their body, in hospitals, carbon dioxide, it is added, as in it is mixed with oxygen, 95% of oxygen, and then it creates carbogen, which is artificial respiration. Then manufacturing of fertilizers will be carbon dioxide is heated with under high pressure actually to produce urea. Urea is an important nitrogenous fertilizer. So with ammonia under about 200 degrees Celsius, carbon dioxide is heated and it creates a really very important fertilizer. It is actually a nitrogenous fertilizer which is good for your plants. Then I think in fire extinguishers this is pretty easy because in fire extinguishers, first it is used to extinguish fires. Now fire is produced by burning combustion of a substance. So the two conditions necessary for producing air are a combustible substance and a supporter of combustion. With these conditions fulfilled, it results in fire. Fire can be controlled by removing one or more of these conditions. This principle is used to extinguish a fire. So first condition that carbon dioxide fulfills is that it does not support combustion, neither is it combustible. Okay, and second one, it is heavier than air. Again, I'm saying this 1.5 times heavier than air. So it insulates the burning substance by cutting off the supply of oxygen. So what happens is it insulates the burning substance. For example, if paper is burning or like a whole cloth is burning, definitely oxygen is there because without oxygen, nothing can burn because oxygen is combustible. So what happens is carbon dioxide, it insulates the burning substance and it cuts off the supply of oxygen. Thus oxygen is gone and the burning substance it no longer burns. So that is why carbon dioxide is used in the first place in fire extinguishers. Now, to know more about fire extinguishers, wait for my next video on fire extinguishers where I'll be talking about how carbon dioxide is used in fire extinguishers. Until next time, bye.